go ahead and get started. So hi everyone, welcome to today's SciML Webinar presented by Xiaoyu Xie, and session chair will be Dr. Youngsoo Choi. So I'll introduce Dr. Choi, who is the computational math scientist at CASC under Computing Directorate at Lawrence Livermore National Lab. His research focuses on developing efficient reduced order models for various physical simulations for time-sensitive decision-making, multi-query problems such as inverse problems, design optimization, and uncertainty quantification. His expertise is in scientific computing and has various research interests. Thank you for joining us, Dr. Choi. I'll hand it over to you.
All right, thank you so much for the introduction. Okay, today's speaker is Xiaoyu Xie. He is a third-year PhD candidate in the Department of Mechanical Engineering at Northwestern University, working under the supervision of Professor Wing-Kam Liu. Before joining Northwestern, Xiaoyu earned his master's degree in mechanics from the University of Chinese Academy of Science in 2017 and gained professional experience as a computer vision engineering for 2 years. His areas of expertise include scientific machine learning, additive manufacturing, and data-driven modeling. Xiaoyu's current research focuses on the developing robust and flexible artificial intelligence algorithms to discover hidden patterns and knowledge from data in manufacturing, fluid mechanics, and solid mechanics. His research goal is to improve the interpretability, generalization, and the small data set scalability of AI algorithms by incorporating existing scientific insight. Xiaoyu's research has been published in prestigious journals such as Nature and the Computer Methods in Applied Mechanics and Engineering. Xiaoyu has received several first-place awards from the National Institute of Standards and Technology in the AM Bench 2022 challenge for the modeling results in predicting cooling rates, grain structures, and dendritic microstructures. Today, he's going to talk about exciting topic. The title is Data-Driven Discovery of Dimensionless Numbers and Governing Laws from Scarce Measurements. So the stage is, Xiaoyu, it's all yours.
Okay, yeah. Thanks for Dr. Choi's introduction, and thank you for willing to being a session chair for this talk. And also, I would like to thanks for Professor Vince Wanderson, inviting me to be to giving this talk. And thanks for CASE for organization for this event. And one of our co-author, Dr. Raj Samuel, he's a postdoc fellow at our Northwestern University, and he also attended today's seminar. And today I'm going to talk about data-driven discovery of dimensionless numbers and governing laws for scarce measurements. So if you have any questions during the presentation, feel free to interrupt me, and I'm willing to have more conversation and answer your questions. So today's presentation is I mainly talk about our recent paper published on Nature Communication in December 2020. And in this paper, we actually proposed new machine learning algorithms and to accelerate the scientific knowledge discovery. So basically, we combine the power of machine learning and dimensional analysis. And the first key point for our approach is we can discover the dominant dimensionless numbers and governing laws from data. And most of data are from experimental data. And second thing is, it can reduce the high dimensional parameter space into a fewer physically interpretable dimensionless numbers. So you can see it is kind of physically dimension reduction. And let's begin. All physical laws actually can be expressed in dimensionless relationships using fewer dimensionless numbers and in a more compact form. In fluid mechanics, it is well known that Reynolds number is very famous, and we can use the value of Reynolds number to distinguish the flow pattern, like a laminar flow or turbulent flow. And the Reynolds number was discovered by Osborne-Reynolds in 1883. And this number actually relates to 4 physical quantities: the density and the velocity and length and the dynamic viscosity. And by combining these 4 parameters, it can actually have one dimensionless parameters. And this dimensionless parameters is a ratio between initial force and viscous force. Another example is from physics. So in 1945, the first atomic bomb was exploded in the US. And after a few years later, a magazine published a few photographs along the timestamp and and the scale. So after seeing these photographs, a British physicist, G.I. Taylor, actually made the estimation for the power released by the explosion. He estimated that the power is 25 kilotons of TNT. This was actually shocked the military, US military, because this was still secret at that time. So how did G.I. Taylor made the estimation with so limited data? This is because he used dimensional analysis and derived this simple equation about the energy, and he can feed the length and time from these photos and can estimate the energy. And dimensional analysis and dimensionless numbers has been proven to be a very powerful tool for over the years, and it has been applied in many fields: biology, chemistry, engineering, and physics. And more than 1,200 dimensionless numbers have been discovered actually. And there are many advantages for describing a physical system using dimensional analysis. The first one is it can actually reduce the number of parameters, like variables. So for physical systems, we know it can, if a system is related to one physical quantity of interest, like y at here, and the input parameters is like 5 parameters. And for each parameter, we know it has its own dimensions based on its physical meaning. And it is actually equivalent when we reformulate this equation into a non-dimensional form. And we can find the number of input parameters reduced. And the second advantage is that it actually enables coarse scale experiments. For example, when designing this hypersonic aircraft like a X-14-3 plane, and we can actually conduct some small scale experiments in internal laboratory. And all we want to do is to make sure these small scale experiments can accurately reflect the behavior from these full scale applications. So how can we do that? We actually need to make sure the geometric similarity, kinematic similarity, and dynamic similarity. So by ensuring these similarity are the same, we can make sure these 2 experiments are the same. So how can we make sure the similarity? Basically, we only need to make sure the dimensionless numbers are the same, because the dimensionless numbers are scale invariant, even though the scale in these 2 sets of experiments are different. So by ensuring the scale dimensionless numbers are the same, researchers can actually confidently extrapolate the small scale experiments results to the full scale applications. So this actually can significantly facilitate the design process. And the third advantage is it can actually increase physical interpretability. Interpretability is a very hard topic in machine learning and in physics. And dimensionless numbers is actually a ratio between different forces, velocities, energies, or mechanisms. So we can actually understand it, by analyzing the magnitude of the dimensionless numbers and to understand the behavior of the system. For example, in this Pack-Lie number, we know it is a ratio between the convection rate of a physical quantity of the flow and the rate between and over the gradient driven diffusion rate. So we can actually do the order of magnitude analysis and to understand the behavior of this system. And so far we know the dimensions numbers and the dimensional analysis is very powerful and popular. So how can we identify the dimensions numbers? There are generally two ways. So for some classical physical systems, we already know the Goldman equations. Because we already know the Goldman equations, we can actually directly non-dimensionalize the Goldman equation and find the dimensions numbers. Because the dimensions numbers are usually the coefficients for the derivative terms. For example, we know the Goldman equation for laminar flow is Reynolds number, is Navier-Stokes equations. And when we non-dimensionalize Navier-Stokes equations, we can actually find two dimensions numbers, the Reynolds number and the Froude number. But in more general case, we don't know the Goldman equations, and because we don't fully understand the complex the phenomenon. So how can we do that? Like Buckingham pi theorem can actually help us to do that. So for example, in keyhole dynamic, in additive manufacturing involves many different physical processes like heat and mass transfer and fluid mechanics and fluid flow. And among these processes, chaotic keyhole dynamics is a very complex one. And the knowledge for the keyhole motion is incomplete. So we cannot use the first approach to derive the dimensions numbers. But we actually, the classical theorem called Buckingham pi theorem can tell us that it is possible to obtain dimensions numbers from this data. Because we can do some experiments from this additive manufacturing, and we can change process conditions and the material systems. We can analyze the data using Buckingham pi theorem. And the core of dimensional analysis is actually the Buckingham pi theorem. And for every physical systems, if we analyze the causal relationships, we can find that one dependent variable, y, is related to five independent variables. And for each parameters, we actually can analyze the dimension for each parameters. It is equivalent to the non-dimensionalized form. And we should note that there are only 4 fundamental dimensions in nature and science, such as length, mass, and time, and temperature. And for mechanical systems, we usually only use 4 dimensions, length, mass, time, and temperature. So the first key point is any quantity, the dimension of any quantity is a power law for these fundamental dimensions. And Buckingham pi theorem actually tells us how many number of dimensions numbers are sufficient to describe a physical system. And it is not a necessary number. So what is Buckingham pi theorem? It states that if we have n physical variables in these systems, and all these variables can be expressed in j independent physical dimensions, so we only need k dimensions numbers to describe this problem. And this actually leads to another important fundamental invariance called dimensional invariance. So what is dimensional invariance? Dimensional invariance states that all physical laws should be independent after we change the unit systems. If we use different unit systems, we should have the same physical laws. And there are many ways to do dimensional analysis. And here we try to use the matrix form to understand the dimensional analysis. So at first, we need to find all the parameters related to this problem. For example, if this problem relates to n parameters, and P1, P2 to Pn, and all we try to do is to find the unknown function f. So the next thing is we need to analyze a dimension for each parameters. And after do that, we can construct the dimension matrix D. Because we try to find the dimensionless numbers, so we need to solve this linear system, D times W equal to 0. And we actually can split W into a set of bases. And we have a K basis vectors because of Buckingham pi theorem. And this actually is a null space. This is actually a null space. And also you can use a Gaussian animation to find these basis vectors, these K basis vectors. So we know that any linear combination of these K basis vectors should satisfy this equation. So if we try to find the ith dimensionless parameter, and what we should do, we just need to find the power law, and we need to find the power index for each parameter. And this Wj, this Wi is this vector. So to find one dimensionless number, we just need to find one W. And this K number is basically based on the Buckingham pi theorem. And the next step is, because we already reformulate the problem, previously we have n parameters, and right now we have K dimensionless numbers. So we can simplify the problem into another function. And this function is related to K dimensionless numbers. Okay, is it clear? Are there any questions? Okay. And there are actually some two main limitations for dimensional analysis. So the first one is, we know the linear system D times W. This is actually an underdetermined system because we only have 7 fundamental dimensions, but we can have many parameters. So the number of rows, it can be very large. And we cannot find the dominant dimensionless numbers from infinite number of W. And the second thing is, if we only use dimensional analysis, the relationship between these K dimensionless numbers is unknown. And this relationship is typically a nonlinear relationship. So we try to solve these two limitations using a data-driven dimensional analysis. And here I try to compare these two things together. For classical dimensional analysis, the first thing is we need to find a parameter list and construct a dimension matrix as this. And we non-dimensionalize the equation so that we can reformulate the problem into K dimensionless numbers. And the relationship between these K dimensionless numbers is unknown. So how about the data-driven dimensional analysis and our dimensionless learning approach? So the first step is the same. We need to find a parameter list and build a dimension matrix. And second step is we need to collect some data. And these data are usually from experiments. We can collect an n set of data for P1 to Pn. And after that, we non-dimensionalize the equation in a more compact form. So here we only use m dimensionless numbers to represent the system. And in the left side, we use K dimensionless numbers based on Buckingham pi theorem. But here we use m dimensionless numbers because we try to find the dominant dimensionless numbers. And this can be searched from the data. So the next thing is we just need to fit the data and try to identify the best fitting representation for these m dimensionless numbers. And let's give you an overview of this kind of dimensionless learning and data-driven approach. From this parametric space, and we have like a Q dimension. Q is a dependent variable, and we have an independent variable. And we find a set of experimental data. And given this data, here to simplify the explanation, I assume there are only one input dimensionless numbers. And the output Q is already a dimensionless parameter. But you can refer to our paper, like section 1 in the supplementary information, you can find more comprehensive analysis and for a general case. But here, to simplify the explanation, I have these assumptions. So the problem is we try to find a Q equal to F1 pi, and we try to find a pi, and we try to find a F1. F1 is a representation. And okay. And for each pi, it is actually the power law index. And we try to find the power index for each parameter. If we take a look at this problem in details, we can find it is actually a constrained optimization and with L1 regularization. So why we need it? So what is the objective function? So the objective function has two parts. The first part is for a mean square error, and second part is a L1 norm. So QI is a experimental measurements, is a experimental data. It is a ground truth. And FH is a representation for this system. And here, exponential W transpose, this is actually the pi. This is actually a pi. So why we have this L1 regularization? Because we assume the most of the dimensionless numbers should have a simple form. Just like Reynolds number, it's very simple form. It is very simple form. So the power index should be simpler, should be small, and the involved number of parameters should be small. So the first part is try to find the best representation for F, and second part is try to make the dimensionless numbers much more simpler. And after all we try to do is find the best W and the beta. So here is a constraint, physical constraint. D times W should be equal to 0. And the FH actually can have many different forms, like polynomial functions and neural networks, and also can be integrated with SINDy, like sparse regression, because some equations can be like differential equations. And for neural networks version, by combining dimensional analysis and dimensional invariance with machine learning, with neural network, there are several research recently. The first one is Dimensionless in our group, and the second one is from Washington University, from Professor Brunton and Professor Nathan Kutz. They proposed a Bucky Knight. And another one is about also use a neural network and with machine learning and dimensional analysis. So how to solve this problem? We actually use a two-level optimization scheme. This is because there are two kinds of parameters. The first W is related to dimensionless numbers. And we try to make sure these dimensionless numbers have a constraint, D times W equal to 0. And the second coefficient we need to find is beta. Beta is a coefficient for the representation F. So the dimensionless learning actually embeds a principle of dimensional invariance into this two-level optimization scheme. So for the first level, in the first step, we try to fix the beta. We try to fix the beta and try to find the best W for the dimensionless numbers. And here has a constraint for the beta, for the W. In the second step, we given this discovered intermediate W, and we try to find the best beta. After doing many iterations, we can find the best W and the beta at the same time. So this is a two-level optimization scheme. So why we need two-level optimizations? Because there are only small rational powers are preferred for the W. For example, like the -1 and 0.2, 0.5 and 1 or 2. So here, because we prefer some small rational powers, so we actually prefer to use zero-order optimization, like grid search or pattern search. And for the second step, it is kind of like a standard regression problem, and the input is some dimensionless numbers, and the output is like the dependent variable. So it is much more flexible. You can use a polynomial or tree-based method and also deep neural network. So there are many flexibility if you use like a two-level optimization. So here I want to show some examples. The first example is this turbulent Rayleigh-Benard convection. This is a very complex phenomenon in nature, and it is very widespread. So basically, there are there is a container, and the bottom is heated and the top is cooled. So we have temperature difference, and we can measure the heat flux from the bottom to the top. And this phenomenon is related to the height of the container and some fluid properties, and also the gravity. So here we can actually build a parametric space, and here to simplify the explanation, we assume the left-hand side is a NASA number, and we try to find the parametric space, this F, in the end. The next thing is we collect some data. We collect about more than 100 data, about 100 to 150 data. And we construct the dimension matrix. And after that, we use a two-level optimization. The first level is to try to explore the dimension space to find the W. And the second level is to find the best representation, beta. So basically, it's a polynomial coefficient, beta. And first level is to try to find the basis coefficient, because W is related to the linear combination of the basis vectors, WB. So after doing this kind of analysis, like what I demonstrated before, we can actually discover the existing dimensions numbers, like a Rayleigh's number, and the NASA number. And we also can discover some new dimensions numbers, even though we don't know the name, but the relationship between these two numbers is much more simpler. And the performance is also very good. Basically, the R-square score, the maximum for R-square score is 1. And in this example, we demonstrate our method in fluid mechanics. So the next thing is we try to analyze vapor depression dynamics, as I mentioned before. This is a very complex phenomenon in additive manufacturing because it has very complex laser material interaction. And recently, we actually have X-ray imaging to understand the keyhole, this vapor depression dynamics behavior. And this data is come from literature, and we collected data from different process conditions and 3 kinds of materials. So we build the input parameter list like this, some effective laser power and some scan speed and others. And here, the quantity of interest is the keyhole depth. Basically, we want to understand how these input parameters can influence the keyhole depth, because the keyhole depth is a direct measurement for how much energy has been absorbed by the metal. So the parameter space to be explored is this one. And we have 7 input parameters and 1 output parameters. And by using the same method like I mentioned in the fluid mechanics, we actually can rediscover famous dimensions numbers in additive manufacturing. This is discovered by our co-authors, Professor Gan, in 2021. This is a linear relationship to describe these different process conditions and for different materials. And we also can discover some new dimensions numbers and the scaling laws. And all these scaling laws have very simple equation and the simple form, and has very simple relationship. And all the R-square score is very high. In the third example, we try to understand the defects for 3D printing. We know that defects has many uncertainties, so it's very complex to understand it, especially for the porosity in 3D printing. If we zoom in this part, this is a 3D printing a build part. If we zoom in this part, we can see some parts have poor porosity, and some parts has a lake of fusion porosity. So this porosity highly influences the quality of the parts. So how to understand the porosity is very important. And typically people use like energy density. It seems energy density is good, but if we only use energy density to feed the porosity, the performance is pretty bad. The R-score is only like 0.13. If we use like our approach, we can actually, the dimensionless learning can give you like rediscover the existing dimensions numbers like this one. This one is also in the Professor Gann's Nature Communications paper. And we can find the R-score is 0.7, and it relates to two like non-dimensional parameters. This one, normalized energy density, NED, and normalized entropy product. But we also can discover new dimensions numbers. And these dimensions numbers, you can find it only slightly changed the NED and NEP, these two dimensions numbers. But the performance can increase from 0.7 to 0.95. So we can actually have a better dimensions numbers discovered. So in these three examples, I show you how we can use combined dimensional invariance with machine learning to discover some like some dimensions numbers and the scaling law in fluid mechanics and manufacturing. So the next thing is we try to explain how we can combine this approach with the sparse regression like SINDy and can discover the differential equations, because some data are time varying data. So here, if we take a look at a simple equation like a spring mass damper systems.
Xiaoyu, I think there's a question, I guess, about the previous slides.
Okay.
Yeah, so Varun Shankar is asking, how do you select the initial input parameters? How do you ensure you're not missing any influential parameters?
Yeah, this is a very great question. So here you can see we involved 7 input parameters, and the quantity of interest is very clear, and we care about the keyhole depths. But how we choose the input parameters, this is really like first thing is it depends on your like experience, like which parameters will be more important. You will include these parameters, and also we try to test if we involved like more parameters, can our approach can still identify the like the keyhole number, and we find it actually can. And if we remove some important parameters, for example, sometimes we may ignore some important parameters, and can our approach discover the like the keyhole number? We find it cannot give a like a very good performance. So in real applications, if you find your like feeding performance is not good, it can guide you to incorporate more like parameters. And if you incorporate more parameters, it doesn't necessarily influence the performance. It just increases our computational cost. But most of them but this question really depends on your like experience and your understanding for these systems. But this is a really great questions.
Thanks.
Okay, if you have any questions, please feel free to stop me. And the next thing is we try to understand the like how can we combine like use dimensionless learning to discover differential equations. For example, if we take a look at these spring mass damper systems, we already know the Gaussian equations. And if we change the like the mass, spring constant, and the damper and the initial displacement, we can have different curves. So given this time varying data, can we identify only one Gaussian equations? Because this Gaussian equation is this one. So suppose we only have data. So if we use like a sparse regression like SINDy, it is very efficient because it builds the left-hand side is derivatives, first order derivatives, and the right-hand side has a library. Basically, the library relates to different parameters, like different derivatives and some combination of the derivatives. And we try to find the sparse coefficient for this one. It is very great and it is very efficient because this is only a regression problem. But the problem is for each case, for each experiment, for given like a MKC delta, we only have a scalar coefficient. We cannot have a constant expression for this coefficient. So it cannot give us a parametric Garmin equations, even though you can say like we can combine these like a different combination for parameters into this like a library, but it will be much more complex for the library. And genetic algorithms is a very popular way to solve this kind of problem. And because it can go through all the combination for like operator candidates, and it can go through like combination for operands candidates. It can use different approach to do the optimization, but the problem is it is very high. It requires a high computational cost. So how to find an efficient way to find the like a parametric equations? This is our like we try to solve. So basically, we try to combine our approach with a sparse regression and to solve this problem. So for example, if we have 4 sets of experiments, for each set of experiment, we have different parameters like K, M, delta, and C. And we can conduct sparse regression, and we can find only these 2 coefficients are non-zero. And these coefficients are different. So now we can actually formulate the problem into a problem to discover the relationship between the different parameters and the KC1. This is because why the KC1 is different from different experiments. It's because we changed like different parameters. So we can formulate the first parametric space is like this one, KC1 equal to F1 and relates to spring constant, mass, and initial displacement and spring constant. And we can also formulate the KC2 into another function, unknown function. So after the optimization, as I demonstrated before, we can actually find the expression for these coefficients. So we have, and this method is much more simple and efficient. And it also works well for small data set because we add some physical constraint like dimensional invariance to this kind of problem. And more examples can be found in our paper, like Navier-Stokes equation, Euler equation, vorticity equation, and solid mechanics examples. So here I want to demonstrate the example, the fourth example, like the vorticity form of dimensionless equations. So here we try to we can collect some data from simulations. We have different Reynolds numbers, and here we try to rotate the data, and we put them into a symmetric invariant SINDy. And this is because we assume all physical laws should be same if we only change the like coordinate systems. After that, we can find the temporary Garmin equations for this Navier-Stokes equations. And we can find some coefficients are close to constant, but some coefficients are vary with parameters. So for these coefficients are vary with parameters, we can actually use dimensionless learning and build a parameter space and find the representation for each parameters. And we can actually identify the Garmin equations. This is a vorticity form of Navier-Stokes equations. And we also can find the corresponding dimensionless numbers, Reynolds number at here. So let me give you a conclusion. So in today's presentation, the proposed dimensionless learning is actually a powerful tool to discover some physically interpretable features, dimensionless numbers, and equations like a scaling law and differential equations from data. It is much more flexible because we use a 2-level optimization. You can choose a different approach for your first level to discover dimensionless numbers, and the second level to optimize the best representation learning. And we demonstrate the method on noisy and scarce experiment data and also the simulation data. And this approach is particularly useful if your problem involves many like parameters to be adjusted. And here are some references. And first paper is today's topic, and second paper is a Dimensionless, and the last 3 paper is about additive manufacturing and how we do the predictions. And thanks for your attention. I would like to go through the code. If anyone has any questions, I would like to answer it before I go through the code. Okay.
Yeah, does the audience have any question? Oh, there's one question by Shang. He said, in example 3, I wonder what does the R2 improvement over Gant's paper actually come from? The dimensionless number or the learned function f of h? That was his first question. Do you want to answer that first?
Okay, okay, yeah, sure. Yeah, this is a great question. So you can see from this paper, you can see this part is NEP times H over D, and here is like NED, and we just times the NED by like a non-dimensionalized length, like a D's, like D over like a L, and here we just changed like a non-dimensional length. So basically, we can find the performance can be improved. So basically, this is like this is searched from our like a pattern search approach, and this is like optimize the results. So the key idea is by modifying the existing dimensions numbers with some like a simple non-dimensional length, we can actually improve the performance.
Okay. Shang's second question is there any relationship between your data-driven dimensional analysis method and reduced dimension techniques such as PCA?
Yeah, this is a great question. So we say our approach is a physical dimension reduction approach because we actually add a physical invariance into this optimization scheme, and the reduced dimension will be dimensions numbers. And these dimensions numbers is usually a ratio between different forces and energies and mechanisms, so we can understand it. So it's much more interpretable. But if we use a PCA, so even though we can reduce the dimension into a few like principal component, but we cannot understand and we cannot interpret it. So we don't know what is the meaning for these principal components. This is a key point. The key point is the reduced dimensions numbers can be interpretable. This is a key difference.
Okay, and there's another question by Varun. Is there any intuition for how noisy, scarce the data can be to still allow effective learning?
Sure. Yeah, this is actually a great question, but it's hard to answer it. So typically, if you try to discover the scaling law, like because the scaling law, like most of data from experience, and we can assume the scaling law should be very simple, and so we can feed the equation, feed the equation. But for the PD discovery is much more complex because we need to calculate the first order and second order derivatives. So if you have a higher like noise, it will be much more complex. But there are some papers talking about how to reduce like the noisy effect, such as using a neural network to train a surrogate model and to calculate the gradients, like first order and second order derivatives, and they have better performance. So basically, you can have much more like different approaches to do that. Yeah.
All right. Well, I have a question. You're relying on power law to non-dimensionalize, and that's based on the pi.
Yeah, Buckingham pi theorem.
Buckingham pi theorem, right?
Yes.
Is other nonlinear form ever useful? Other than
yeah,
power law, it's okay. The power law seems very simple in I guess it works surprisingly well,
Yeah.
but does it
So-
cover everything?
Yeah. So the key idea is we try to so from the beginning, we have n parameters, and each parameter has its own dimension. For example, if only the first parameter and second parameter involves like a dimension for length, and if we try to find a dimensionless number, we definitely need to like P1 times or P2 or P1 over P2. We need to like have some constraint to this. So if we try to do this, we definitely need to use a power law to do that. And this is actually some natural, the discovery in science and nature. So for example, in nature, we have in Earth, we have many creatures from mice to giant whale. It has different natures, but we can actually use some two-dimensional numbers and we can describe all the creatures on the Earth. So this is some assumption. So basically we assume the problem can be described in dimensionless form and the relationship will be much more different, simple. But your question is pretty important. So here we try to use for the second level, we try to use like a more flexible approach. It can also be simple like polynomial. It can also be like a complex deep neural network, because a relationship can be nonlinear and complex. But the input should always be like dimensionless numbers. So this is the trade-off and the assumption.
There's another question by Eric. Can you rediscover physics laws such as Maxwell equation?
Yeah, we haven't do this kind of discovery, but if you are willing to do that, I think you can do that. Yeah, I think you can do that.
Okay. Another question by Chan. Could you explain a bit more about how to use the non-dimensional number in additive manufacturing discovered by your method?
Okay, yeah. So how to use it is because additive manufacturing is very complex, because if we change different parameters like laser power and scan speed and laser beam radius, it's very hard to understand how these parameters influence keyhole depths. Especially we try to extrapolate our discovery equation to more general material systems and general process conditions. So this kind of approach actually discover if we discover two-dimensional numbers and can describe this, describe different systems and different conditions in a much more simpler way, we can actually understand if we try to have a lower keyhole depths, we can use this range of keyhole number, and if we try to have a higher keyhole depths, we can use different range of the keyhole number. So basically, it can facilitate the material design and the process design for this kind of approach by understanding this. So basically, it's just like for Reynolds number, we can directly use Reynolds number to distinguish the laminar flow and turbulent flow. And the same thing for the additive manufacturing. We can use the keyhole number to distinguish the depths of the keyhole depths.
Sounds good.
Yeah, sorry, I have one question, sorry.
Well,
Okay.
So on where you showed the improvement where the R squared goes from 0.7 to 0.9, I guess I have two questions about that. What do you consider a bad R squared? How low does it have to be for you to say, okay, this is a very bad fit? And then the second question is, so what was added there is a d cubed over L cubed. Do you have some interpretation of that? It looks like a volume ratio of some sort. Like, have you dug into the physical meaning of that d cubed over L cubed?
Which one DQ you mean?
When you change from any, I think it's any p to any d times d cubed over L cubed in the bottom right figure, when the R squared increases, I think you changed by adding a length, dimensionless length there.
Oh yeah. Here I list the length at here. basically there are only three like length parameters. First one is like, I would like to answer the first question. So what kind of like R-square score is a good one? So in more general case, if the R-square is below 0.7, it means nothing. In more general case, but this actually depends on your problem actually. So for some problem, it's very easy to have a very high like R-square score, but the performance, but like if you fit it, you can find like 0.95, but it is still not good. You can have a very like have a better R-square score. So it really depends on, but the general case is below 0.7 is not very good. And for the improvement from 0.7 to 0.95, it's actually, we try to explain it in our paper. And we actually only know the changes is we change like, we times the NED or NEP with some non-dimensional length, but yeah, it's hard to explain the physical meaning for this like this non-dimensional length. Yeah, this is a.
Okay, there is another question by Varun. Are there any system that cannot be described with dimensionless parameters? Have you tried this approach on those to see what happened?
Yeah, this is a great question. So basically, you know, in the first slides, I mentioned we have already discovered more than 1,200 dimensionless numbers in different fields like chemistry, biology, physics, and fluid mechanics, all these areas, even though like society and like COVID-19, we have some dimensionless numbers. So when we try to like solve one problem, we assume we can discover some like dimensionless numbers. But if we cannot discover dimensionless numbers, we actually don't know whether it is because there is no dimensional numbers, or it is because our method or our data is not good. So this is really hard to answer.
Well, I think what Varun is asking is, you know, by human intuition, it's impossible to come up with a dimensionless parameter, some physics problem, but maybe your algorithm is able to discover dimensionless parameters. Yeah.
Yes. Our approach is try to like, if you use Buckingham pi theorem, like follow this Buckingham pi theorem, this really like requires you have a very extensive understanding for the problem, so that you can know like which k dimensionless numbers is very good for your system. This is very hard to choose. So we try to use a data-driven approach and to leverage a computational power and to search it and to find it and give you some solutions. Yeah, thank you for Dr. Choi.
Okay, so have you tried that for those such systems?
Yeah, in our paper we tried eight engineering problems like fluid mechanics, additive manufacturing, defects, and solid mechanics. Yeah, we already try as much as we are possible, but we encourage others to try more examples.
I have a question about the two-level optimization scheme. You know,
okay,
some computational math questions. Does this two-level optimization obviously, you know, taking some sort of fixed point iterations? Is this algorithm guarantees to converse?
Yeah, this is a good question. Yeah, actually cannot guarantee the converge. So we need to have many different initial points. And
also, in your experience, sometimes it doesn't converse, so you have to try this new.
Yes, you're right. So basically, if we have like some initial like W, so basically it cannot converge to the global optimum. It will stuck at the local optimum. So we have to have more initial points and analyze the results. So basically, we need to have a model selection or equation selection after we doing many initial different initial points. Yeah, I think this is this point is very hard to solve. Yeah.
Yeah. Some mathematicians needs to be involved.
Yes.
All right. I don't see any other questions in Q&A.
Okay. Okay.
But
Yeah,
Keith, can they unmute themselves and then ask, or I don't know how.
Yes. If we need someone to unmute, we can ask them to unmute themselves. So they can mention that in the question if they want to have a conversation, and we will have to promote them.
Okay. Well, yeah. Anyone?
Yeah, Kate, do I need to explain the code?
That's right.
Yeah, we can go to the code review if there are no more questions.
Okay.
Well, looks like there's no more questions. So
okay, yeah, I can share the code. So basically, we have a online we have a code in GitHub. You can search PyDimension in GitHub, and we also have an online documentation. So basically, there are some tutorials. So for the first part is scaling law, and the second part is for the PDE and ODE discovery. So in this documentation, you can find some overview and some tutorials, and find the code. And if you find the paper is helpful, you can cite the paper. And here I want to demonstrate how to use a code, like the pattern search. I mentioned a pattern search, but I will not give you go into the details of pattern search, but you can refer to the paper and find the pattern search. So here, give you an overview of the two-level optimization. If you want to run the code in the computer, it is also fine, because you can directly click here to open it on Colab or in the binder, and you also can click that here. So basically, you can click on Colab, and if you try to run it on Colab, please uncomment these two lines, because you need this help you to import your data set. I can run all. And the first part is try to import some parameters, Python packages. And this part is try to incorporate a data set. And let's go through this main function. So here I try to demonstrate the code in keyhole dynamics problems. So the first thing is you need to import the data set. The data set is in this a data set and keyhole. If you go through the data set file, you can find this spreadsheet, and it has different columns. Different columns have different involves different parameters. This is a keyhole depth, and you need to set your input list. Basically, it's a title for each parameters, and this is a parameter list that we care about. So after that, you need to assign your dimension matrix D. Here we have 4 dimensions, 4 fundamental dimensions, and we have 7 independent parameters. And this one is a basis function. So we can find in this example, we have 4 fundamental dimensions, and we have 7 parameters. So we will have 3. So K is 3, and we have 3 basis vectors. So here is 3 columns. For each column is a basis vectors. The degree means order of the polynomial function. So you can use this function dataset class to create your dataset, and it can help you to split the dataset in training set and test set. And after that, you can build your model and feed the model. And also after that, you can return to the R-squared score and the power index for the dimensions numbers, and also obtain the coefficient for the polynomial function. And this is try to predict the perform model in training set and data set test set. So after that, we can do the visualization. So in this case, we can find this is a Pi1 and Pi2. You can find the training set and data set fits very well in a linear relationship. Even though these data are from literature and from experiments and from different process conditions and different 3 kinds of materials. So this is and if you want to go into the details how we do the optimization for the pattern search, like you can go through the details at here. So this is an example for like a scaling law discovery. And another example for like a ODE discovery for like a spring mass stamp persistence. You can go through this one. So basically there are some descriptions and imports libraries. And this class is to, firstly, the bulk class is to implement a sparse regression. And second, this one is try to calculate the derivatives. And after that, we need to prepare some data set. The data set involves different, the sparse regressions results for different set of experiments. So for example, if we have like, we can have different different parameters for the spring mass stamper, and we can solve the equation. This is an example. And after that, we can feed the equation, and we can build the library, and we can feed the library. So the main paragraph is main code is like this one. So you feed the library, you choose the like parameter space, and we can collect the data set. This data set is actually involves different experimental data, simulated data for spring mass stamper system. And this is an overview for that. This 4 columns involves different parameters, and these 2 involves like the coefficient discovered, non-zero coefficient discovered. So after that, we can recover the coefficient for the KC one, and you can directly run it and set the input parameters and set the output parameters and build the dimensions for the dimension matrix for the input and also for the output. Basically find the basis vectors, and you can do the optimization and find the like the best coefficient. And we can do the same thing for the like the second coefficient. So basically, if you want, you can like run this code, and we have some like tutorials for this code, and you can run it. Okay, yeah, I think that's all for the code explanation. Do you have any questions?
Very nice. Do you have any questions from audience? looks like a really nice documents you put on the web.
Yeah, everyone can get access to it by searching the Dimension GitHub.
Do you have a other? I mean, you know, in the paper you have put many other examples, right? Like the
we have
example. Is it
other examples at here, like
available in GitHub?
Yeah, in
Nice.
GitHub.
So if I understand correctly, the key assumption in here is the Buckingham pi theorem, and if so that's assumed to hold, and if that doesn't hold, you can't just generalize this, I guess, dimensionality reduction method to other systems, right?
The key difference for dimension, like a classical dimensional analysis with Buckingham pi theorem, is Buckingham pi theorem gives you like the sufficient number of dimensions numbers. So you have k dimensions numbers. But here we only use, like we try to find the dominant dimensions numbers. For example, even though like 3 dimensions numbers are sufficient, but maybe we only need 1 dimensions numbers to describe the system. The feeding performances will be already good. It is possible. So here we try to find a less than like k dimensions numbers. This is a key difference. And the key innovation is like we try to combine some fundamental physical invariance with machine learning. Like this is actually a physical constraint problem, and to do the accelerate the discovery. This is a key like a philosophy for our approach.
I guess the question for another question for you is what do you think is the most exciting application that you see this being used in? What's sort of the dream or what you'd want to achieve with this method?
Yeah, I think the additive manufacturing is like the very exciting applications, because most of my research is doing additive manufacturing, and it's pretty complex to understand the phenomenon, like the big process. And if we and our like the discovered dimensions numbers, like the modified keyhole number and the modified like NED and AEP number, it can actually have better performance. So this is actually exciting. But if you have more general case, for example, if you have a problem involves different adjustable parameters, it also fits well for this kind of approach, because we try to find the relationship between the dependent variable and the independent variables. I think chemistry and fluid mechanics are the two important application areas.
Are there any other questions from the audience? If not, yeah.
It can be applied to, the dynamics which does not have a known governing equations, such as like COVID or the human behavior.
Yes, I think so.
Those can be also applicable, right?
Yeah, because there is like a dimensions number for COVID-19. I know that, like this dimensions number, I don't know the name, I don't remember its name, but it tells us how much like the spreadability for the like one person, like it's already dimensions numbers. And another key important thing is like sometimes for the core scale experience, we can only do like small scale experience. If you do like a machine learning to train it, you cannot generalize well for a large scale. It definitely cannot. But if you incorporate this dimensional invariance as a constraint, it can do that, because dimensional analysis naturally fits the like a core scale experiments. Yeah. So this can also be an application.
Very nice.
Yeah, and maybe just to probe that COVID example a bit more. In that case, you will have a lot of parameters that are not dimensionless, that do not have dimensions, like population and susceptibility to disease or stuff like that, right? Like, would you have to change your fundamental matrix there where you have length, time, and temperature and whatnot for that?
You're right. You're right. So the key point for our approach is like if we have like in the additive manufacturing problem, we have 7 input parameters, and each input parameters has its own dimension. But for a general case, if you have like most of the parameters does not have dimension already, so even though you add this dimensional invariance, it cannot help you. So this kind of approach like cannot help you to do that well, but it can only help you to like if you have like most of the parameters have its own physical dimensions. So this is some limitations, yeah.
Okay, then I guess if there are no more questions, I have a question for Dr. Choi, who I guess you work a lot in dimensionality reduction. What do you think is the most exciting, I guess, path forward as people try to find different ways to do dimensional reduction in general, and I guess with the context of this work as well?
Oh, well, I don't know, with, these days, thanks to the advances in machine learning, traditionally in dimensional reduction community, we have just looked at the linears, tried to find out the compact linear subspace, which covers the underlying data or dynamics. But a lot of times, if the data is coming from hyperbolic problems where the advection phenomena characteristic can be prevalent, then those linear subspace representation has been really challenging to capture those dynamics in compact manner. But thanks to the advance in machine learning, now we don't only have to limit ourselves to the linear subspace region. We can expand ourselves to nonlinear manifold region, and there are exciting research going on in our community, so that the compression you can do can be really practical, and even more compression is possible, even with the advection dominated problem. So how is it related to what Youngsoo presented today? I do think it's related. In some sense, it is nonlinear manifold reduction. If you try to connect this the nonlinear manifold reduction to what he's presented today. So it would be very interesting to find out, those connections and expand from there. So definitely, I'm planning to discuss more about that with today's speakers. Yeah.
Okay, thank you for that perspective. I think there are no more questions for today. Thank you, Xiaoyu, for presenting. Thank you, Dr. Cho, for being session chair. This was a very interesting session with lots of great questions. I will mention what we have next week. So for next week's webinar, we have Leon Gerard and Michael Shebela, who will be talking about variational methods for estimating wave functions. And the session chair will be Wei Luo Ren. So thank you all for coming, and see you next week.
Yeah. Thank you.
Bye.
Thank you.